It's a quick run through of a copper nickel cell simulator. You can see the basic setup here. There's a copper anode or cathode, depends, we'll see, dipped in some copper nitrate solution. And then there's a nickel electrode dipped in nickel nitrate solution. And right now we're running this as a voltaic battery. We can assume that these electrodes are fresh. And now some of the nickel gets oxidized to nickel 2. When that happens, if you look carefully, there's some electrons coming out. So these electrons will go down the wire. They will become available here. And if a copper ion comes in, it can get reduced. The electron's not so well visible to become copper. So the copper electrode gets bigger and the nickel electrode gets smaller. Here's a cheat sheet. This is the cathode. And this is the anode, where oxidation happens. Cathode is where reduction happens. And the whole circuit is closed by a KCl bridge. It's called KNO3 here, but it's really KCl in the demo. So electrons are coming in this direction, right? And so we're watching what happens here. This gets more positively charged because we have these positive nickel ions coming in. And so chloride ions flow out of the salt bridge to neutralize this. What we don't see here on the other side is we're losing copper ions, cations, in the copper cell, half cell, and so then potassium ions will stream out. Okay, so that's the direction it goes if we just put a wire on it, and now we can reset this and go in the other direction. So then the figure is not correct. We would have to actually apply a electrical potential there. For some reason this is very fast, but anyway, now the copper gets oxidized. When that happens, electrons are provided to the wire. They come in here, and so when nickel ions reach the nickel electrode, there's electrons to reduce them. So now we're losing positive charges in the nickel half cell, and so the potassium flows out of the salt bridge instead of the chloride. On this side, reverse is true here. It's not shown. Chloride will come out here to neutralize the copper cations that are made over here. This electrode's almost gone, so I can reset and then run more in that direction. The simulation doesn't pay attention whether the stoichiometry is correct, and that's fine because this is a microscopically small part of the electrode, so there might be higher or lower rates going on elsewhere. Same here, same here. We're not showing the bulk situation. So that was it, a quick run through of this simulation. I can quickly say how I made it. The image was made with Gemini Pro, so Nano Banana Pro, and the simulation is a single HTML file in JavaScript, which I don't know, so I gave the specification and I tried different LLMs to rate me this, and I actually forgot which one this is. So I tried Gemini and Claude and ChatGPT. I suspect it's Claude. Okay, and some things to do to fix. As I said, this should be KCl the way it's shown here. Potassium nitrate would be nice because these are nitrate salts already. Really, if I run it in this direction, I should also show the electric potential that we're applying across the cell. That's basically, the cathode and anode changes, so that shouldn't be on that diagram If we were super fancy, we would also change the color of this. This is not by accident, so nickel actually is, nickel 2 plus is greenish, and copper 2 plus is pretty blue. And of course, once this is running at appreciable speed, the colors would change, and at one point we could even deplete all the copper ions in this half cell if we're going one direction, or all the nickel in this cell. On the other hand, we can also totally deplete the cathode and the anode if we run it too long. I'm sure this wouldn't happen because we would also deplete the salt bridge, and at one point copper ions might come in here, or nickel ions in here, and then you don't have separation of the two species anymore, and so then you would break the cell. I think that's it in terms of things to improve, and it was fun to make. And it will be interesting to do one more thing, which is to open up this wire and then just have stochastic reduction and oxidation at both electrodes, right? So if I oxidize a couple of copper atoms here, then this becomes too positive, and this becomes too negative, and then it would drive it in the other direction. But you can have a couple in one direction or the other direction, just randomly happening. That happens when the cells are open, and it also happens when they're closed. But once there's a strong potential, then you're favoring one over the other direction. Those are my thoughts. Thanks for listening.